Okay, student, welcome back to the next class. So, in the previous class we know a very important concept that if a matrix is normal, then they produce the orthogonal eigenvectors. Today we will go with a very important concept, we will start a very important concept which is called diagonalization of a matrix, which is equally important, diagonalization of a matrix. What is mean the diagonalization? So, a matrix is represented like this. These are the elements this is not diagonalized because all the elements here, if it is non-zero, then this is not diagonalized. The diagonalized matrix is something where only we have the diagonal elements, other elements are 0. For example, this is the diagonal matrix, this is a general matrix and this is the diagonal matrix. Now, the question is it possible to diagonalize a matrix? So, let me first write the thing then. So, a matrix, given matrix A can be diagonalized, say D, a matrix A, it is diagonalized to a matrix D with a transformation, similarity transformation. Now, you should appreciate what is the meaning of similarity transformation with suitable P. So, if I able to find a P, so in last class we find that these A and D are called similar matrix because they are related with a similarity transformation, which is this that we defined already in the previous class. Now, this similar matrix has a property important, this D matrix has an important property that it has to be diagonal. So, in order to diagonal that, I need to have a proper P to that. So, what should be the P? That is the important question here. What should be the P? How to generate a P? P is nothing but, let me say V1, V2, V3 V1, V2, V3, Vn, these are the corresponding eigenvector of A. I know that. Okay. I try to find out what is P. So, before that I know this is my eigenvectors. Now, if I form a P with putting these vectors like this, this column vector here, this column vector here, this column vector here, then I can form a matrix P. This is the P which can diagonalize. So, that means I will need to form a P which is made of the corresponding eigenvectors in this form. So, now okay, let me explain more what is V1 component wise. It is say V11, V12, V1n. What is V2? Say V21, V22, V2n and so on. Now, I will put this V thing here. So, my P matrix will have the form V11, V12, V1n. These are the nothing but the corresponding matrix corresponding vectors, eigenvectors element. V21, V22, V2n, Vn1, V n2 V nn. So, this is my P, this. Okay. So, now I have my P matrix, which is formed by the matrix which is the nothing but the eigenvectors. So, now few things. So, P, if I operate over E I, what I am getting? So, let me write it clearly. So, my P is V 11, V 12, V 1n, V n1, V nn. I operate with E I. So, P is a matrix that I operate over E I. So, just I am trying to find out what is the value of these things, which is interesting. So, E is a natural basis. So, I will have this. As a result, what I am getting? This multiplied by this other 0, this multiplied by this, only this column will retain, other things will vanish. So, I will have V 1. In the similar way, if I do A 2, I will have V 2 and so on. So, in general P E I, if I operate, I will get a vector V I, which is the ith eigenvector. Fine. So, now another important thing, what is P inverse P E I, which is P inverse V I. P inverse V I is coming out to be E I, which is also an important outcome. So, P inverse of V I is nothing but E I with this. I require that because I need to. So, let me write this outcomes here. So, P inverse of V I is E I. I will going to use this expression to prove that they will going to diagonalize, this similarity transformation will going to diagonalize. So, now after having that, let us now write what is AP now. AP is a matrix multiplied by the P matrix. P matrix I write in this form: V 1, V 2, V n. Fine. So, P is a matrix which I define like this, which is a combination of all the column matrix that I have, which is the corresponding eigenvector of A. So, I have this matrix in my hand. Now, I operate A over P. So, if I operate these things, so what happened? A will operate over that. So, it will gives you lambda 1 V 1, lambda 2 V 2 to lambda n V n. It will give in this, because A is a eigenvector, V are the eigenvectors. So, V I is lambda I V I, no problem with that. So, I will have another vector, another matrix form, this is also a matrix form with this condition. Now, if I operate P inverse over AP, because this I defined as my diagonal matrix D. If I operate these things, then what happened? P inverse will be operated over lambda 1 V 1, lambda 2 V 2, so on. So, let me erase this, because we are not using this anymore, because we know how these things are forming. Right, I got this. Now P is operated over this, lambda is a constant. So if that is the case, I can write lambda I P operated over Vi, lambda 2 P inverse operated over V2, lambda n P inverse operated over Vn, like this. Now this quantity I already figure out earlier, this is the same quantity, so I will just replace this. So it will be lambda I Ei, lambda 2 E2, lambda n En. This is my, according to my notation, this is D matrix. I can write this D matrix in this compact form. Now I will expand this form and you will readily understand what is going on. So I get D matrix like this, I just replace Ei to the matrix form. So what will be lambda I multiplied by Ei? So lambda I, let me write it here first, lambda I Ei is how much? Lambda is a constant multiplied by 1 0 0 0 0. So it will be simply lambda 1 0 0 0 0, this. So my first thing is 0 0 0. What about second thing? In the second case, the first term will be 0, E2 is here. So instead of having 1 here, I have 1 here. So lambda 2 will be placing here. So it will be lambda 2 0 0 0 0 0 in case of, and so on. So you can see that this D matrix is now diagonalized. This D matrix is now diagonalized. Not only that, we get a very important information out of that, these diagonal elements. These diagonal elements, whatever the diagonal elements I have here, these diagonal elements are the corresponding eigenvalues. So diagonal elements is lambda I are the eigenvalues. So essentially what we are doing, we diagonalize, we find a recipe to diagonalize a matrix. Not only that, if I able to diagonalize the matrix, then in the with the similarity transformation that we have, we need to find a P and also a P which contain the inverse of that. It is not necessarily that always a P inverse exists. There is a possibility that it will not going to exist. So it should be a non-singular matrix. So if I able to figure out my P properly with the eigenvectors, then I can diagonalize, and this diagonal element will be the corresponding eigenvalue. So this is the recipe. Now we will going to use this recipe to figure out and try to diagonalize something, one matrix. So let me try to do that quickly. So I need to choose a suitable matrix. So let me choose a suitable matrix. Say A is 2 6 0 minus 1. This is the matrix I take. I need to diagonalize this matrix. So first thing is that need to find out the eigen values and eigenvectors. So 2 minus lambda 6 0 minus 1 minus lambda is equal to 0. I have a straightforward equation, lambda plus 1 by lambda minus 2 is equal to 0. This. So my eigenvalues are lambda 1 is minus 1, lambda 2 is 2. Again you cross verify 1 and 2, if I add it will be minus 1. Here also I have the same quantity, so trace is matching. If I multiply it will be minus 2, the determinant of this matrix is also minus 2. Now I need to find out the eigenvectors out of that. So 2, 6, 0, minus 1, x1, x2, say I find it for I want to find it for say minus 1. So minus 1, x1, x2. What expression I am getting? 2x1 plus 6x2 is equal to minus of x1. If I take it here, then from that I will have 3 of, so right way it will be 3 and then 6 it will cut. So x1 plus 2x2 is equal to 0. So x1 is equal to minus of 2x1 x2. So my first eigenvector for this, if I put x is equal to 1, x2 is equal to 1, then x1 is equal to minus of 2. So my first eigenvector, say v1, is coming out to be minus 2, 1. Coming up to be minus 2, 1. Now I will do the same thing for other. For lambda is equal to 2. For lambda is equal to 2, I need to replace this with 2. Now I need to calculate once again. So 2x1 plus 6x2 is equal to 2 of x1. So here we find one, so x1 is cancel out. So I find 6x2 is equal to 0. So that means one equation I get x2 equal to 0. If x2 equal to 0, in the second expression if I do, then I will also get the same thing where x2 is equal to 0 equation will come. So that means I can put x1 arbitrarily, say I put it is 1. So now this equation, this eigenvector v2 is something like 1, 0. It is like 1, 0. So now after having these two eigenvectors here, I can form my P matrix. So let me now form my P matrix. So what is the mechanism or what is the recipe to form the P matrix? The P matrix should be like V1, V2. So here my P matrix V1, which is minus 2, 1, and V2 is 1, 0. So I can form my P matrix readily. Next thing is to form the P inverse. So inverse, you know, in order to find the inverse, you need to make a adjoint and then divided by the date of these things. So first I need to find out date of P. I believe all of you know how to calculate the inverse of a matrix. So I am not going to spend time on that. So date of P is equal to minus 1, and P transpose, if I make a P covector matrix, is something like this. It will be 2 for 0, 1 it will be minus 1. When I do this, this will cut and this value will put here. So, here this value will be negative sign, put will be here. For this value I will cut this and will be negative sign, put here, and for this value I will put this here. So, my value is this. Now, I need to make a transpose of this. So, transpose of this, it will be 0 minus 1 minus 1 minus 2, the same thing. So, if I do, then P inverse is come out to be 1 by date of these things, which is minus 1 multiplied by 0 minus 1 minus 1 minus 2, and my P inverse supposed to be 0 1 1 2. After having the P inverse, the next important thing is that please check whether whatever the P inverse you are getting or I am getting here is the correct thing or not. So, first I will going to check that P inverse is minus 2 1 1 0 and P inverse is 0 1 1 2. 2 into 0 minus 2 into 0, 1 into 1. So, I have 1 here, minus 2 into 1, 1 into 1, 2 into 1, this is 0, 1 into 0, 0 into, so it is 0, 1 into 1, so it is coming. So, P inverse, whatever the P inverse I get is the correct one. So, I now get P inverse, So, once I get the P inverse, then my job is almost done. P I get, P inverse I get, so my job is almost done. So, next what I will do that I will just plug it this to find out what is that. So, my recipe is D is equal to similarity transformation of A like this. So, I find my P inverse, I find my P. So, I will just plug it there and try to find out. So, my D matrix, which should be the diagonal matrix, should be P inverse, which I get is 0 1 1 2, A, which is my original matrix, 2 6 0 minus 1, and finally P, which is minus 2 1 1 0. I need to calculate that. This will give me the diagonal matrix if I am right. 0 1 1 2, this is 2 into minus 2, it is minus 4, 6 minus 4, so it is 2, 2 into 1 2, 6 into 0, so it is 2, 0 into minus 2 0 1, so it is minus 1, 0 into 1 1 into, so it is 0, and then 0 into 2, this into this, it is minus 1, 0 into 2, this is 0, 1 into 2, this into 2 into minus 1, it is again 0, 1 into 2, 2 into, so it is a diagonal matrix. First conclusion. Second thing is that please look to these elements, which are the eigenvectors that I figure out. One is minus 1 and another is 2. So, I find a recipe which is very important, that using which you can figure out how a matrix can be diagonalized. The same recipe can be applied for any dimension of matrix. As I mentioned in my last class, every time I am taking a 2 by 2 matrix, because it is easier to calculate in the blackboard, but when you do that, sit down in your room and try to calculate so you can do that for 3 by 3 matrix also, the recipe will be exactly the same. So, once again I remind what actually I do here, that if a matrix is given to you, first you calculate the corresponding eigenvectors, and then from these eigenvectors you can form a matrix P. Next step, this is a step 1, this is a step 2. You find, you can construct P. Step 3, you need to find out P inverse, and step 4, you make a similarity transformation of this P inverse A P, which gives you the diagonal matrix, where the diagonal elements is nothing but the eigenvalues of A. This is related to a similarity transform, and P is a matrix that you figure out with this recipe. So, with this note, today I would like to conclude my class here. So, this class you learn a very important thing, that how a matrix can be diagonalized. As I mentioned, that first, in order to do that, you need to just figure out your eigenvectors, and from that eigenvectors you need to form a matrix called P, and with the similarity transformation of the P you can diagonalize your matrix. So, with this note, so let us conclude this thing. In the next class we will carry forward with more on the matrix things, some specific matrix and similarity transformation and all these things, and also try to understand one important concept is called rank of a matrix, or another important thing which is Cayley-Hamilton theory, if time permits. So, with that, so let us conclude this class. So, see you in the next class.